Hi everyone. So today I'm trying out using my headphones as a microphone. So we'll see if that audio comes out sounding any better than when I used my laptop as a microphone. Fingers crossed. So yesterday in our video, we were talking about limits. So I just want to remind you about the definition of a limit, and then we'll get into more discussion about limits. So recall from last time. So last time we introduced this idea of a limit, and we said that the limit as x approaches a of a function f of x is equal to a number L, or L could be possibly infinity or negative infinity, which are technically not numbers. So limit of f of x as x approaches a is equal to L if as x approaches a, the function, so like the outputs of the function, approach L. So either that would mean that the outputs are getting closer and closer to a particular number, and that would be if L was a number like 5 or 1 or 0 or whatever. If L was infinity or negative infinity, when we say that f of x approaches L, that would mean that f of x is either getting bigger and bigger and bigger, going up like 1,000, a million, a billion, or getting smaller and smaller and smaller would be going to negative infinity. So like negative 1,000, negative a million, negative a billion. So we talked about yesterday one particular way of evaluating limits. So I want to write down the method that we talked about yesterday, and then I want to talk about some shortcomings of the method that we were using in yesterday's video. So ways to evaluate the limit as x approaches a of f of x. So first method, like we talked about yesterday, is basically to plug in numbers closer and closer to a. And basically observe, see what happens to f of x. So there are a couple of things to keep in mind when we're talking about, see what happens to f of x and, what kind of numbers you're plugging in. You do need to be careful. So there's a couple of points I want to write down here that we didn't really talk about last time. So one thing is, if you're plugging in numbers, make sure that you're plugging in enough numbers to really get a sense of what's happening with the function. So basically, if you were just to plug in like 1 or 2 numbers, you might not really be able to see the trend enough. So you really want to be plugging in numbers that are getting closer and closer to A, not just like a few numbers close to A, but you want to kind of have this trend of getting closer to A. So that's like where we did yesterday, maybe like 0.1 and then 0.01 and then 0.001 if you're trying to get closer to 0. So you want to make sure your numbers are getting closer and closer to that number. And then you want to make sure that you can actually observe a trend in the outputs. So, it might be the case if you just plug in a couple numbers, you might not be able to tell what's going on. So I just want to write that down. So make sure that you are plugging in enough different numbers to observe a trend in your outputs. So that's one thing. And the other thing, and I guess this isn't really like something to make sure, it's just something to be aware of. Sometimes, even if you do plug in plenty of numbers, this method still kind of falls apart. So plugging in numbers is kind of like, it's the first thing I like to teach when you learn limits, because I think it gives you a good kind of intuitive sense of what's going on with limits. But we'll see that there are some places where it's actually not going to work so well. And eventually we'll be using other methods that are a lot nicer and cleaner and faster. So I just want to say sometimes this method doesn't work. So I just want to show you one quick example, kind of like a counter example that shows you how what we were doing yesterday could fall apart. So let's look at a specific example of this. So let's say that you are trying to find the limit as x approaches 0 of sine of pi divided by x. So we'll talk about this a little bit more today, but we mentioned last time that typically when you're taking a limit, you're taking a limit because you can't just plug the number in, right? So you can't just plug 0 in because then you would have pi divided by 0, which is undefined. And so if you're trying to take sine of something that's undefined, well, then the whole thing is going to be undefined. So that's why you can't just plug in 0, and that's why in this case you would probably want to take a limit instead to kind of explore what's going on when x is close to 0. So let's say that you tried to make a table and you filled out the table with the advice we had above. You made sure that you tried out plenty of different values and your values were getting closer and closer. So we could do like -0.1, -0.01, -0.001. Okay. So what would happen in this case, so let's say that, for example, you did the first one. So sine of pi divided by -0.01. So -0.01, another way of writing that is negative, oh, sorry, I meant to do 0.1. That's our first value. So another way of writing -0.1 is -1/10, right? That's how you write 0.1 as a fraction. And then -1/10, well, if you're dividing by -1/10, that's actually the same thing as multiplying by 10, right? Because dividing by a fraction is the same as multiplying by the reciprocal of that fraction. So that means that the stuff inside of the sign, we could actually write as -10 times pi. And so if you remember what the deal is with the sine function, sine of any integer multiple of pi is always going to equal 0. And there's a couple ways to think about that. One is if you know what the graph looks like, it passes through the x-axis at any multiple of pi. So at pi, at 2 pi, at 3 pi, at 4 pi, at -pi, -2 pi, -3 pi, -4 pi, etc. So we get 0. And so basically, because of what I just said, you're going to get 0 for all of these, because for this next one, you would have pi over -1 over 100, and then that would become sine of -100 pi. That's also a multiple of pi, and so you would also get 0. And then the next one, you would get -1000 times pi, and you'd also get 0. And then same thing with the positive ones. When you plug in all these positive numbers, you would get 0, 0, 0. So you might look at this and say, oh, okay, the limit must be 0. So I'm going to write that down, and this is going to be kind of a wrong conclusion. So does the limit equal 0? You might guess that. But let's look at what the graph of this function actually looks like. So this is the graph of sine of pi over x. And maybe just make it, that actually doesn't really help. So you can see it looks very crazy. Basically what happens is the closer and closer x gets to 0, the more this function kind of just oscillates back and forth between 1 and -1. So it gets really crazy and intense the closer you get to 0. And basically, this is an example of a function where the limit does not exist. And the reason it does not exist is basically because this function is just so crazy that it kind of goes back and forth way too much. But notice, even here I put f of 0.1 equals 0, f of 0.01 equals 0. So plugging numbers, it still appeared like you're getting 0, but the problem was we just happened to choose like lucky examples. So because we thought we were just picking like the most kind of easy number to plug in, but we were actually picking examples of numbers that that specifically just kept giving us 0. So my point is that basically you can't always rely on plugging numbers as like your final method for evaluating a limit. So in this case, maybe I'll just write this back down. So actually, the limit does not exist. Look at the graph. Okay. So the next method that we're going to be talking about is actually looking at the graph of a function. So second method for evaluating limits is basically to graph your function f of x. And basically similar idea to what you're doing with plugging in numbers, right? When you're plugging in numbers, you're plugging in x values and you're seeing what happens to the y values. So similarly, when you're looking at the graph, you're going to be looking at where are the y values getting closer to as x gets closer to whatever place you're taking the limit. So you're going to graph the function and see what happens to the y values on your graph, because those are your outputs of your function, as x gets closer to a. So this is basically what we're going to be focusing on today. So we'll be coming back to this. And then there's just one more method I want to mention, because this is what we're going to be getting into later, which is basically using algebraic methods. So we'll see that actually this third method is kind of the best method. Again, I like to do first plugging in numbers and looking at graphs because they're a little bit more intuitive, and I think there's a lot to gain from them. But really, at the end of the day, the algebra that we're going to learn tomorrow and next week is going to be kind of the best way to actually evaluate at least most limits. So this will be tomorrow and next week. Okay. So today we're going to be looking, like I said, at limits of functions, looking at their graphs, but we're specifically going to be focusing on piecewise functions, because piecewise functions bring up some kind of interesting stuff when it comes to limits, and I just think it's a good thing to also review for most people how to graph a piecewise function. So we're gonna look at a couple different examples here. So let's start with this one. So let's say our function is f of x is equal to 2x plus 1 if x is less than or equal to 0, and negative x squared if x is greater than 0. Okay, so what are we going to be doing with this function? We're going to be finding a few different things. So I'm going to write them down and then we'll come back to them. So we're going to be evaluating the limit as x approaches 0 from the left. We're going to be finding the limit as x approaches 0 from the right. We're going to be finding just the overall limit. And then finally, we're going to be also evaluating what is f of 0. Okay, so all the stuff that I just wrote down in orange, you could do that without graphing your function. You could just look at this, this piecewise function and kind of use the equations to figure out. So for example, for the limit from the left, well, if you look at this piecewise function, you use the top equation, right? 2x plus 1, that's the equation you use when you have numbers that are to the left of 0, right? It says if x is less than or equal to 0. So if you wanted to plug in numbers, you would want to be plugging them into your top function for the limit from the left. And then similarly, you would want to be plugging into the bottom function for the numbers from the right. And then um, the limit without left or right, remember that you have to look at whether they agree or not, and that will tell you what to put there. And then finally, f of 0. Well, if you look at these two equations, the equal part is on the top equation. So you'd actually use the top equation to evaluate f of 0. That being said, I think being able to graph these is really valuable, and I really would recommend graphing piecewise functions in order to evaluate their limits. And then later on, we'll actually look at an example where I'm not even going to give you the equation, I'm just going to give you a graph. So you should also be able to find limits just by looking at a graph when there's like no equations even involved. Okay, so let's remember how to sketch something like this. So basically, remember, a piecewise function it's called a piecewise function because you have different pieces to it. And so you want to kind of just sketch each piece on its own. So the first part of this function is, it says 2x plus 1. So what I'm going to do is I'm just going to graph 2x plus 1, and I'm going to ignore the if x is less than or equal to 0 part for a moment, just so that we can get this thing graphed. And once we have it graphed, then we can come back and focus on that restriction. So what does 2x plus 1 look like? It's a line, it has a y-intercept of 1, it has a slope of 2. So that means it's going to go like this, and it's going to go like this, something like that. So now we can look at the part of the equation, or the part of the function after where it says if, and that tells us the domain, basically, of each of these parts. So the first part, you're only supposed to use that part when x is less than or equal to 0, and so that means we want to get rid of this first part. We only want the part of this function where the x values are less than or equal to 0. And then the other part of the equation is negative x squared. So that would be a parabola that has been reflected. So I'm just going to start graphing that. So again, let me make that a little better. So again, I'm graphing like the whole thing, and you don't have to do that, but I think sometimes just to like focus on that first. So I just graphed an upside down parabola. But then we look at the actual restriction, and we see that we're not supposed to use this negative half. It's just supposed to be when x is greater than 0. All right, there's one more thing we want to add on here, which is you should put kind of open and closed points to denote which part of the graph you're using at that kind of meeting point, right? So 0 is the place where it switches from one of the parts of the graph to the other. And so what we want to do is we want to put a closed dot on the first function, and we can put a little arrow there too. And the reason we put a closed dot is because you're supposed to use that equation when x is equal to 0. It says when x is less than or equal to 0, so we put a closed dot there. And then the bottom equation, well, we put an open circle on that one because we're supposed to use that one only when x is strictly greater than 0. And this is going to bother me, so I'm just going to redo that so that it's, okay, actually an open circle. And we can put an arrow here too. Cool. Okay, so now let's look at these limits, and let's try to see like what would you be looking for on the graph if you were evaluating these limits. So when we're evaluating the limit from the left, we're seeing as we get closer and closer, so as we're kind of bringing our x values closer and closer to 0, where are the y values heading? And the answer is the y values are heading towards 1, right? The closer and closer our x values get to 0, the closer and closer the y values get to 1. And so therefore the limit is 1. Now from the right-hand side, if we're now looking at x values that are getting closer and closer to 0, so we're like starting here, kind of zooming in towards 0, zooming in towards 0, we can see that the y values in this case are also heading to 0. So one thing I just want to really emphasize here is that it does not matter where the circle is open or where it is filled in when you're evaluating limits. When you're evaluating limits, you're just looking at the trend of where the graph is heading. It does not matter what's happening at 0. That does not matter at all when you're taking limits. It does not matter what is happening at x equals 0. It only matters what's happening when you're close to 0. And so when we're evaluating this limit from the right, even though we have this hole in our graph at 0, that doesn't matter. We're just looking at, we're kind of ignoring that. And we're just saying what's happening when we're close to 0. So when you're close to 0 and above 0, it looks like the graph is heading to a y value of 0 as well. And so that's why the left-hand limit is 0. So now for the overall limit, well, we have the left and the right-hand side disagree, right? One of them is 1, one of them is 0. And so that means that the overall limit, just the limit as x approaches 0, that limit does not exist. Okay, let's look at f of 0. So f of 0, if you want to evaluate that by looking at the graph, that's where you do care about what is filled in, because the reason that we filled in the 1, the 0, 1, and we left 0, 0 open was actually specifically to denote that when x equals 0, that's when you use the top equation. And so that tells us that f of 0 is equal to 1. And you could confirm that using your the formula up here, right? If you looked at which equation are you actually supposed to use when x equals 0, you would see that it's the top equation. Okay, so let's do another example of graphing a piecewise function and using it to evaluate limits. So the second one is going to be g of x is equal to, so it's going to be sine of x if x is, actually, let me rewrite this. So it's going to be sine of x if x is basically anything other than 0. And then it's going to be 1 if x equals 0. So let's think about what this graph is going to look like. So basically, let's start by just sketching the graph of x, and then we can go back and see what we need to get rid of. So sine of x goes through the origin, right? The y-intercept is 0. And it goes up, and then it comes back down and goes through pi 0. And then similarly, on the other side, we see something similar happening, but kind of reflected, right? Because sine of x is an odd function. And so basically our graph looks like this. So that would be if we were just graphing sine of x. But notice that it says it's only equal to sine of x if x does not equal 0. And so what that means is we want to just add in a hole in the graph at x is equal to 0, because that is the one point where we're not using this, this equation. Okay, so what do we put instead? Well, this tells us that g of x is supposed to equal 1 if x does equal 0. And so that means that when you plug in an x value of 0, you should get a y value of 1. And so that means that we need to have a point up here at 1. Okay, so similar to the last one, we are going to evaluate the limit as x approaches 0 from the left of this function. We're going to do the limit as x approaches 0 from the right of this function. We're going to do the limit as x approaches 0 overall of the function, and then we're also going to evaluate g of 0. Okay, so the limit from the left. So we're basically looking at plugging in x values that are just to the left of 0. So we're looking at getting closer and closer to 0 from the x direction. And basically what we see is that the graph is heading towards a y value of 0. Even though the graph does not have a filled in point at 0, it's heading towards there, right? If you ignore the point at 0 and see what the general trend is, you would guess that the graph is going to 0. And so that's what we put as our limit. And in this case, we have the same thing happening from the right side, right? Like the difference is in the example we did earlier, the two pieces of the graph did not match up, right? So we had something different on the left and different on the right. In this case, the two parts of the graph do match up. And so we have the same thing happening from the right. As you're tracing in, coming from the right, looking at values just above 0, the y values are also heading to 0. And so that tells us that because these two agree with each other, they're both equal to 0, overall the limit of this function is 0. However, g of 0 is not equal to 0, right? If you look at what actually happens when x equals 0, the output is 1. And so g of 0 is equal to 1. So again, just to say it again, because this is like the most important thing I think to understand about limits is that limits don't care about what's happening at the number that you're looking at. They only they only think about what's happening close by. And so even though g of 0 equals 1, that has no influence on what the limits are, because the limits are just thinking about, other than at that point, where is the graph heading? So I want to look at one more example, which is actually not a piecewise function, but just to really kind of make a point to basically emphasize the point that I was just making. So let's say now that you were just looking at sine of x on its own. So let's sketch that graph again. So sine of x is going to look like this. I guess maybe I shouldn't put arrows because that seems to suggest it's going to keep going up, which is not the case. Okay. So let's say we wanted to do all those limits. So the limit as x approaches 0 from the left, the limit as x approaches 0 from the right, the overall limit as x approaches 0, and then finally h of 0. So like I was saying, it really does not matter what happens at 0. We only care about what's happening close to 0. And so because the function that we graphed in purple and the function that we graphed in green, they're identical except for that one point at 0, which was filled in on this one and which was moved up on the previous one. And so these answers for the limits are actually all going to be the same. It's still going to be 0, it's still going to be 0, it's still going to be 0. Because regardless of the fact that the point is filled in at 0, it's still heading towards 0. We really don't care whether that point is filled in or not. So one thing that I mentioned that I want to say again is that typically when you're taking a limit, it's because your function is undefined or something funny is going on at that point. But sometimes you take a limit when there's nothing funny going on at that point. So in this case, the thing that we got for our limit is actually the same thing you would get by just plugging 0 in. So sometimes that happens. It's really about ignoring, again, what's happening at that point. It doesn't matter if the function looks normal at that point. It doesn't matter if the function has a point removed. You're just looking at where the graph is heading aside that point. Okay, so just a few more examples. So I now have a graph for you to look at where, let me make this maybe a little bit, bigger if I can. Oh, that's not what I'm trying to do. Okay, I'll just do that. My marker is probably going to get a little thicker now too, so let me change that. Okay, so I want to do some limits looking at this graph. So now let's say that this function is called f of x. So let f of x be the function graphed over here. So I want you to find a whole bunch of different limits. So I'm going to write them down, and I would recommend pausing the video and seeing if you can yourself figure out what the answers are for these, and then we'll go over them together. So we're going to do the limit. I'm going to use a different color. Let's do the limit as, back to the thick marker. Let me make that a little thinner. Okay. So let's do the limit as x approaches -3 from the left of f of x, the limit as x approaches -3 from the right of f of x, the limit as x approaches -3 of f of x, and then also f of -3. And then similarly, we'll do the same thing at -1 and at +1. So I'll write those ones down as well. So let's also do the limit the limit as x approaches -1 from the left of f of x. And by the way, try not to get confused with the multiple negative signs. So it's -1, like literally just the number -1. And then the negative and the plus, those just mean from the left and from the right. They're unrelated to whether the number is positive or negative. So then we'll do the limit as x approaches -1 overall of the function. And then we'll do f of -1. And then the last one we'll do, what's a color I've not used? Let's do green. So the last one we'll do is 1. So we'll do the limit every time. Sorry about that. What happens is when I zoom in, it makes the markers all get like a lot thicker. It's probably not a big deal, but once I already started changing it, I felt like I had to keep changing it. So then we'll do the limit from the left at 1, the limit from the right at 1, the overall limit at 1, and then f of 1. So again, pause the video, take a minute to try these yourself. I'll put it back up here so that you can actually see the full picture, and then we'll go over them together. Okay, so let's look at -3. So the first one is asking for the limit as x approaches -3 from the left. So that means that we're looking at coming in like this, right? We're looking at x values that are getting closer and closer to -3. And so if we look at the trend of where the graph is heading, it's heading towards a height of 2. So now looking at from the right, well, now if we're coming in from the right, our graph is heading towards a height of 3. So the limit from the right would be 3. So that tells us that the overall limit does not exist. So DNE is shorthand for does not exist. So it does not exist because the two sides don't agree with each other. The graph doesn't have a general trend. It only has a general trend from the left and from the right. So now to find f of -3, now we just look at where is there actually a point filled in the graph, right? Because when you have an open circle like this, the whole reason that circle is there is to tell you there's no point there, right? That's what that symbol means. It means there's no point here. And so if you're looking at an x value of -3, you can't use this part of the graph. You have to go above and say, okay, f of -3 is +3. Okay, so next one, let's do -1. So if we're looking at -1 from the left, again, we're coming in from the left side of -1, so we're going like that, and we're seeing where are the y values of the graph headed, and they're headed towards a height of 1, right? That's like the trend of where the heights are headed before it gets to that hole. And similarly from the right, when we come in, the graph is heading towards a height of 1. And so that tells us that overall, the limit is 1. However, and actually maybe let me just say one more thing. So that means that ignoring the point at -1, the graph does have this overall trend, right? It's on both sides, it's heading towards the same point. And that's why we get a limit here and we got does not exist in the other case. Okay, so now looking at the at f of -1, well, we have a hole in the graph at a height of 1, and so that tells us that the actual point on our graph at -1 is 4. So we're looking at this point here to tell us what f of -1 is. Okay, last few, and these ones bring up something slightly different. So first thing is the limit as x approaches 1 from the left. So if we look at this, we're coming in this way, and we're seeing that the y values are getting closer and closer to 5. So the limit as x approaches 1 from the left is equal to 5. Now from the right, this is where something a little bit different is happening. So if we're coming in towards 1 from the right and we're going closer and closer to 1, the graph just keeps going up and up and up and up. And so that means that it has a vertical asymptote at 1 on the right-hand side. And so our limit in this case is positive infinity, because the closer you get to 1 on the right, the higher and higher the graph goes. So what this tells us is that overall, the limit does not exist because we see conflicting things. On one side, it's going to 5, the other side, it's shooting up towards infinity. So finally, f of 1, in this case, well, if we look at this part of the graph, we see a hole, right? So there's no point at x is equal to 1. on that part of the graph. And then if we try to look at the other part of the graph, well, that's a vertical asymptote. So it's actually never going to touch x is equal to 1. And so the bottom line is that if you look, like if you go to an x value of 1 and you kind of look above it, there's just no point at an x value of 1. So that tells us that f of 1, I'll just use my shorthand here, does not exist. There is no f of 1 in this function. All right, so that is it for today. So your worksheet today is going to basically give you a lot of practice with problems very similar to what we did in this video. And then tomorrow, like I said, we will be getting into evaluating limits using some algebra tricks. So I will see you all next time.